Hi everyone, it's Wednesday, so it's time for another Chem Help ASAP live stream. I hope you're doing well on this Wednesday. So today, as you can tell from the title, we are going to be working with percent yield calculations. Now, this does mean we are going to be calculating what percent yield is, but I find that students have a more difficult time taking a given percent yield and then going back and calculating reactants. So we're going to spend more time using a percent yield that's given, but we will do a calculation where we first find percent yield as well. So we're going to kind of go what I consider forwards to find a percent yield, and then we'll do calculations where we also work backwards and work back to find our amount of reagent. So thank you, OG Benchmarks, for being my moderator tonight. And let's go ahead and get started. Okay, so here's our first, again, simple problem. Chromium and sulfur react to form chromium 3 sulfide. When 175 grams of chromium react, 324.26 grams of chromium 3 sulfide is formed. What is the percent yield of this reaction? And they give us a reaction, and it is already balanced, so we are go. It's not quite balanced, actually. It's almost balanced. Ooh, they almost had me there. Let's put in this blue. All right, so this should have an 8 right there. Yep, and now we are balanced. Actually, that's probably just a typo on my part. I forgot to put the 8 in. Now we have a balanced chemical equation. It's always good to check those things. Otherwise, your stoichiometric ratios are off. Okay, so what we've got is, I guess, first of all, let's identify this as a stoichiometry problem. So I know it's stoichiometry because I am given information about about a reactant, about one compound, and I am really asked about the percent yield, but you can see I'm given information about different compounds, and I am relating these with a balanced chemical equation. So at some point, we're going to do some stoichiometry in this problem. Now, again, remember, when we're doing stoichiometry, any type of stoichiometry, whether it's percent yield or limiting reagent or solution stoichiometry or gas stoichiometry, we're always going to go through moles at some point. So I do want you thinking in terms of moles as soon as you see stoichiometry come into view here. Okay, so this is a stoichiometry problem. Specifically, we're calculating the percent yield of this stoichiometry problem. All right, so we know how much of our chromium reacts, and we're also given how much of our product is formed. Now, let's first just maybe write down what our formula for percent yield is. So percent yield is, and I might be, okay, I just want to make sure I'm not running into like my video feed here, is our actual yield over our theoretical yield. That is really messy. And of course, that is times 100%. Okay, and that is underneath my video here. That is times 100%. So we have an actual yield. The actual yield refers to you go to the lab, you run this reaction, how much of a product do you actually get? The theoretical yield refers to the yield you would predict just doing stoichiometry, just doing this on paper. So what we have here is we have a yield. So is it our actual yield or is it our theoretical yield? Well, in this case, because this is what is formed, this is our actual yield. So we have been given this numerator right here, which means to calculate our percent yield, we need to get a theoretical yield, or we need to figure out what you would predict just based on stoichiometry. Now, just based on stoichiometry, we need to know how much reactant we're starting with, right? Well, they gave us how much reactant we're starting with. So what we're going to do is we're going to do what I would call a simple stoichiometry problem, because this is not a limiting reagent problem. We're going to go simple stoichiometry. We're going to start with our mass of chromium, and we're going to figure out our mass of chromium 3 sulfide, again, for our theoretical yield, because this 324.26 grams is our actual yield. So it's really important when you're doing these problems to keep straight what is the actual yield and what is the theoretical yield. Okay, so let's go ahead and start this. So we're going to start with our 175 grams of chromium. Again, because we're doing stoichiometry, we need to be in moles. So our first step is going to be convert grams to moles with our molar mass. So our molar mass of chromium, here we go, per 1 mole of chromium. All right, so now that I am in moles, I'm going to use my stoichiometric ratio to predict my moles of product or chromium-3 sulfide. So I want to make sure that my moles of chromium cancel, and I am going to moles of chromium-3 sulfide. Again, this 8 and 16 is just coming from the balanced chemical equation. And now finally, I have my moles of chromium-3 sulfide. I'm going to convert that into grams because I was given grams in the problem. Whenever you're doing percent yield, you want to make sure that your units match for the actual yield and the theoretical yield. So my actual yield is in grams, so I want to make sure my theoretical yield is also in grams. So my molar mass, that is chromium-3 sulfide, is 200.1874 grams. Okay, before we plug this into our calculator, let's just make sure that all of our units are canceling like we expect them to cancel, and that we have, in the end, we have the unit that we have been trying to get to. So my grams of chromium cancel. Here my moles of chromium cancel. My moles of chromium-3 sulfide cancel, and I am left with grams of chromium-3 sulfide, which is exactly what I wanted. So that's always a good sign when your units are canceling and you get what you expect. If ever you're doing that cancellation and something goes wrong, go back and check your calculation because something has gone awry there. Okay, so if we put this in our calculator, we get this number right here. Again, I'm going to give us lots of decimals because we're not going to round yet because we're not at the end, but I do want to mark where where my sig figs are. So let's talk about sig figs real quick. So we're doing all multiplication division here, so we just want to find the number with the fewest sig figs. So I'm starting with my 175.0. That has 4 sig figs. My molar mass has 1, 2, 3, 4, 5, 6 sig figs. Of course, my mole ratio has an infinite number, and this molar mass is 1, 2, 3, 4, 5, 6, 7 sig figs. Okay, so it looks like my 175 grams of chromium is going to limit me. Specifically, it's going to limit me to 4 sig figs. So that means I'm going to be rounding at that 8 right there. All right, so again, I'm not going to actually round it. I just put my mark in because I am not finished with my calculation. So let's go back and now let's calculate our percent yield. So our percent yield, again, I am just plugging in my numbers into this formula. So my actual yield, this is again, if you were to go in the lab and run this reaction and measure how much you get, this is how much you actually get. And that was given to me in my problem. That, is 324.26 grams of chromium-3 sulfide. And now I'm going to put this over my theoretical yield, which I just calculated. That is 336. Again, I'm going to write down all of these decimals, but I'm going to make my mark to remember that I am rounding to that 8 right there. And then this is times 100%. Okay, so now we just plug it into our calculator. And when we plug it into our calculator, we get 96.8 0.25431%. But of course, let's round to the correct number of sig figs. So let's count up our sig figs. So for our top number, we have 1, 2, 3, 4, 5 sig figs. And our theoretical yield has 4 sig figs. So we're limited to 4 sig figs. So we need to round at that 5 right there. So let's round this properly. 96.25%. And that's it for your unit. So notice with your unit, and I should have written this down. This is also grams of chromium 3 sulfide. So what we've got going on here is the units cancel and your percent yield is unitless. Now this is really important because it doesn't have to be in grams. You can calculate a percent yield if you use moles for both. So I could have converted this grams into moles and ditched this last step on the stoichiometry problem. That's totally fine. That's perfectly fine. You can absolutely do that. You just want to make sure for your percent yield that your units in your numerator and your denominator should match exactly. Not only grams, but also whatever compound or species you're talking about. Okay, it doesn't look like there are any questions, so we are going to go on to our next problem. So that one that we just did was a very much straightforward how to calculate percent yield. So this problem, we're going to start doing what I call working backwards. So let's just read this problem first. Potassium chlorate decomposes into potassium chloride and oxygen gas when heated. The percent yield of this reaction is 81.67%. If 130 grams of potassium chloride is needed, how many grams of potassium chlorate is required? Okay, so, and they didn't give us a reaction, so we're going to have to provide the reaction. Let's actually do that first. Let's provide our balanced chemical equation. Okay, so potassium chlorate is going to be this. It is going to decompose into potassium chloride plus oxygen gas. Okay, now let's balance this equation. This one is, at first you think, okay, potassium and chlorine are balanced, but oxygens are not. So in this kind of situation where you have a 3 and a 2, usually if you just reverse and make a multipliers, it works. So now I have 6 oxygens on both sides, which is great, but I need to rebalance my potassium and chlorines. So that should be a 2 there, and just double check. All right, this looks like a balanced chemical equation. Okay, how do I know that this is going to be a stoichiometry type problem? All right, so we want to make sure, or we want to look for information on 2 different molecules, and we want to connect them by a balanced chemical equation. So we were given 130 grams of potassium chloride, and we were also given the percent yield, and we were asked about grams of potassium chlorate. So again, we're given information about several different species. We are connecting them with a balanced chemical equation. So we are going to be doing stoichiometry at some point in this problem, which means at some point we're going to need to convert to moles. Okay, let's now dive into how we are actually going to do this. So in this case, we know how much is needed and we know our percent yield. So what this means is we're going to need a little bit of extra, right? So if this was 100% yield, then all we would need to do is take this 130 grams and predict how much reactant we needed. But it doesn't quite work like that because obviously most reactions don't go to 100% like this. There's usually some waste. And if you've done your Gen Chem labs, you see this. You've probably calculated percent yields in your lab, and you're not going to get 100%, but hopefully you get close. So what I am going to do first is I'm going to use my percent yield calculation to figure out what my actual yield needs, or sorry, what my theoretical yield needs to be. So again, percent yield is equal to the actual yield over the theoretical yield times 100%. Remembering actuals when you go into the lab, and theoretical is what you do with stoichiometry. All right, so I actually need 130 grams of this. I need to figure out what my theoretical yield is. Okay, so let's just plug in what we know. So we know our percent yield is given to us in the problem. So I'm going to put 81.67% in. We know what our actual yield is. I actually want 130 grams of potassium chloride. I don't know what my theoretical yield is, so I'm just going to call that X, and then I'm going to multiply that by 100%. Okay, so all we have to do at this point is we just have to solve for X. So we just need a little algebra, and our X equals 159.1772, and that is grams of potassium chloride. Remember, your units are going to match when you calculate a percent yield. Okay, let's do sig figs, because of course I wrote down a lot of decimal places, but we're not going to need all of them. So I have 4 sig figs here. I also have 4 sig figs in my 130. And this 100%, that's got an infinite number. That is exact. So I need 4 sig figs, my answer, which means I'm going to round to that one right there. Okay, so this is my theoretical yield. This is my stoichiometric yield if I'm just doing the calculation. So I can take this amount of potassium chloride and do the stoichiometry and figure out how much of my reactant I need, my potassium chlorate. So now we're going to do our stoichiometry problem. So starting with my theoretical yield, my 159.1772. Okay, so first step, because we're doing stoichiometry, is to convert to moles. And that molar mass, 5513. Okay, and per 1 mole. Now that I have moles, I'm going to use my mole ratio to predict my moles of potassium chlorate. And that is 2 moles of potassium chloride to 2 moles of potassium chlorate. Okay, love it when those ratios go to 1 to 1. Now that I have moles of potassium chlorate, I need grams because that is what my problem asked me for. So I have one more conversion to put in here, and that molar mass is 122.5495 grams of potassium chlorate. Okay. Whew. All right, so let's make sure that units are canceling like I expect them to. So my grams of potassium chloride, yes. My moles of potassium chloride canceling, my moles of potassium chlorate, and I'm left with grams of potassium chlorate, which is what the problem asked me for, so my units are lining up just like I want them to. So now let's put this in the calculator and let's get our really long decimal, and then we'll round to the correct number of sig figs. Okay, so this answer is 261.659. Okay, so we're getting I went ahead and put down a lot of decimals here. We obviously do not need all these decimals, so let's talk about sig figs. So my starting mass of potassium chloride, I need to round to that 1, which means there are 4 sig figs. My molar mass here has 6. My mole ratio, of course, has infinite, and this molar mass has 7. Okay, so my mass of potassium chloride is going to limit my answer. And it's going to limit it specifically to 4 sig figs, so I am rounding at that 6 right there. So let me just write this with the correct rounding. 261.7 grams of potassium chlorate. Okay. Let's make sure there are no questions. Okay, so this is an example, again, of how to work backwards. So if you're given the percent yield, how do you then figure out how much of a reactant you need to add? Now, this is very much what you would do in a lab situation. You know how much you want to make. You know the percent yield of the reaction, so how much of your reactants do you put in to make sure you can produce the amount that you want to produce? So it really ties in quite nicely to the lab and also the real world. These are calculations that are done just all the time. Okay, let's go on to our next problem. All right, so let's read it first. Mercury 2 bromide is formed by the following reaction. Okay, and so they have given us the equation. That's great. The percent yield of the reaction is 62.4%. How many milliliters of mercury and bromine is needed to produce 50 grams of mercury 2 bromide? Oops, that should have been, that's an error there. The density of mercury is 13.6 grams per milliliter, and the density of bromine is 3.10 grams per milliliter. All right, so we've got a similar problem, but we've got a little bit of a twist in this one. This one is not asking for grams. It's asking for volume. It's asking for milliliters. So when you see volume, there are a couple of ways you can go with volume. Volume can be a part of a gas. Well, we don't have any gases here, so we're not going to be using any gas laws. Volume can be part of a concentration calculation, but we have no concentration calculation here. And lastly, volume can also be a part of a density calculation, which we do have. So this is why they give us the density of both mercury and bromine, because they are both liquids. We're going to have to use density as a conversion factor to convert from grams to milliliters. Okay, so that's kind of a little bit of information to tuck away. We are going to use that later. How do we know this is a stoichiometry problem? Okay, kind of a big sign is, of course, you're given a percent yield of a reaction, but we have been given information about mercury 2 bromide. We are asked information about mercury and bromine, and we are connecting all these compounds with a balanced chemical equation. Actually, we didn't check to make sure this is balanced. Let's check and make sure. Yes, this is balanced, and this is a 1-to-1, which always makes our stoichiometry just a little bit easier. So we are going to use the percent yield, then we are going to do some stoichiometry, and we're going to do some stoichiometry with density. So let's walk through this, because we're going to have to do multiple calculations, because we need to figure out how many milliliters of mercury and how many milliliters of bromine we need. So we're going to have a couple of calculations going on here. Okay, so let's start with our percent yield. So percent yield. All right, remember this is your, I'm writing it down backwards. This is your actual over your theoretical. I got a little bit ahead of myself, didn't I? Times 100%. All right, so we know our percent yield. They gave it to us, 62.4, oh, there's a decimal, 0.4%. And that equals our actual yield, which is, we want to produce 50 grams. 50 grams of mercury 2 bromide. We do not know our theoretical yield. That's what we're trying to find. And of course, still that's times 100%. So all we need to do is solve for this theoretical yield. Again, just like we did in the previous problem, we just need a little bit of algebra. So our theoretical yield, I should have made this x, that would have been a lot easier. Okay, so our theoretical is, again, giving lots of decimal places, more than we need. Okay, is 80.1282 mercury 2 bromide. Let's talk sig figs. So we have 3 sig figs in our percent yield. We have 3 sig figs in our mass. And of course, our 100 is exact. That's got infinite. So we need 3 sig figs in our theoretical yield, which means I'm rounding at that one right there. But again, I am not going to round yet, because I don't want to introduce rounding error into my final answer. Okay, so we know our grams of mercury bromide, and we need to now predict milliliters of mercury and milliliters of bromine. These are going to be 2 separate calculations. However, we can tie this together. I think it might be easier. Again, there are a couple ways to go about this, but what I want to do is I want to first convert this grams into moles, because then I can take those moles into both mercury and into bromine. So I think I'm going to do that first. Again, there are a couple different ways to do this. You can string along 2 longer calculations if you like. You will get to the same place. The important thing is it makes sense to you, and it's organized in your mind and you know where you're going. That's totally fine. Okay, so I am first going to convert this grams of mercury to bromide into moles. Let's see, that molar mass is quite large. 398 grams of mercury 2 bromide over 1 mole. Okay, so this is going to give me lots of 2s. 3, 3, 2, 5. Okay, so that is plenty of decimal places. But again, we'll mark where we're going to round for sig figs. So originally I'm rounding here. That's 3 sig figs. My molar mass is 1, 2, 3, 4, 5, 6 sig figs. So I need to round to 3. I am rounding at that 2 right there for my moles of mercury bromide. Now that I have my moles, I just find it easier to jump straight into the stoichiometry. So that's why I wanted to convert to moles first. Again, stoichiometry equals moles at some point, and now we are at that point. So let's do the mercury first. Why not? It really doesn't matter which one you do first, but starting with 2, 2, I need to make sure I don't drop any of those 2s, are moles of mercury 2 bromide. Let's predict our milliliters of mercury. Okay, so the first thing I need to do is I am in moles, so I am going to use my stoichiometric ratio to go back to mercury. Great thing about this is it's 1-to-1, so it makes the math really easy. Those 1-to-1s are just, I love running across those. Okay, so now I am in moles of mercury, but I need to get to milliliters. How am I going to get to milliliters? So I know that if I'm in moles, I can get to grams really easy, right? We do that all the time. We just use the molar mass. But can I get from grams to milliliters? Yes, I can, but I'm going to need the density. Well, the problem gave me the density. So you see the units of density are grams per milliliter, which means you can use density to convert between grams and milliliters. In this case, I'm actually going to convert grams to milliliters. So I've got my moles of mercury. Let's first get that to grams of mercury using the molar mass. So let's get this molar mass in 200.59 grams of mercury. And now let's use the density to convert my grams to milliliters. Again, make sure you're writing your units down because it's very easy to get this flip-flopped. So we are actually dividing by the grams of mercury per 1 milliliter. All right, let's check our units. Let's make sure everything cancels like we want it to. Moles of mercury 2 bromide, moles of mercury, grams of mercury. I'm left with milliliters of mercury, which is what the problem asked me for. That's fantastic. Let's get an actual number here. Okay, again, with lots and lots of decimal places, 3.2792. That is milliliters of mercury. Let's talk sig figs. Okay, so this was rounded to that last 2 that has 3 sig figs. My molar mass, not molar mass, my mole ratio has an infinite number of sig figs. I got ahead of myself. This molar mass has 5 sig figs and my density has 3 sig figs. So, yep, 3 is the one I want. I want to round to 3 sig figs, which means I'm rounding right there. So my final answer with the correct number of sig figs, 28 milliliters of mercury. Okay, great. So that's mercury, but we also have to do bromine. The good news is we're going to do bromine in the exact same way. We're just going to have different numbers in for bromine because it has a different molar mass and it also has a different density. I need to give myself another page here. Okay, so still starting with my moles of mercury 2 bromide. This is why I converted to mercury 2 bromide. So let's start with this. 2, 2, 3, 3, 2, 5. That is my moles of mercury 2 bromide. So using my stoichiometric ratio this time, so I'll pop back. I'm going from mercury 2 bromide to bromine, but again, it's a 1-to-1 ratio, so it makes it really easy. So let's get that in. Again, now that I have moles, I'm going to go back. You can see down here with mercury, we went to grams and then we went to milliliters. So I'm going to do the same thing, but I'm going to have to use the molar mass of bromine and, of course, the density of bromine. So first, let's do the molar mass of bromine, convert our moles to grams. 159.808. Whoops, that's Br2. And then now that I have grams, I'm going to use the density to convert to milliliters. Again, make sure you're careful with your units here, especially when the grams ends up being in the denominator. I see a lot of errors at this point when students do these problems. Again, they're not writing down their units. Okay, let's check units since we've just been talking about it. Okay, so the moles of mercury 2 bromide cancel, moles of bromine, grams of bromine, and I'm left with milliliters, which is what I want. So let's get an answer from our calculator, and then we will round to the correct number of sig figs. All right, so this moles is rounded right there. That was my reminder. That has 3 sig figs. Infinite. 1, 2, 3, 4, 5, 6 sig figs and 3 sig figs in my density. So again, I am rounding to 3 sig figs, which means I'm rounding right there. So my final answer is 11.5 milliliters of bromine. Okay, that one was kind of a little bit long, but let's check and make sure there are no questions. But again, you see how you're doing stoichiometry, but then you just have to figure out usually your end game. And for this end game, we had to get to volume. Okay, I've got one more problem here for percent yield. This is going to be our most challenging problem. So let's read it first. It's kind of a long problem. I think I'm probably going to need an extra page again. Okay. Boronite, Cu3FeS3 reacts with oxygen gas according to the following reaction, and they gave us this kind of monstrosity right here. Definitely not dealing with a 1-to-1 ratio. The percent yield for this reaction is 72.35%. Sulfur dioxide gas is collected and has a pressure of 815 torr at 25 degrees Celsius in a 75 milliliter vessel. How many grams of boronite is needed to produce this amount of sulfur dioxide? What pressure of oxygen should the vessel be charged with to produce the sulfur dioxide? And we can assume the volume of the vessel and the temperature are constant. So it sounds to me like if you're doing this in the lab, you've got this vessel, you're going to throw in some of your boronite and you're going to charge that vessel with a certain pressure of oxygen gas, and then you're going to let the reaction run. This is actually really similar to the problem we just did. So let's first identify this as a stoichiometry problem. All right. Percent yield is kind of a dead giveaway, but we were given information here about our sulfur dioxide gas, which is right here, and we're asked about grams of boronite, and we're also asked about pressure of oxygen. So we're given information about one species, and we're asked about another species, and we're connecting all of these with a balanced chemical equation. Okay, so again, we're going to need moles at some point because we've got to do stoichiometry. Now, just like we did before, so remember in our previous problems, we are going to use the percent yield. We're going to find the theoretical yield for this. But we have a little bit of, again, a problem, a little bit of a twist here. So we've dealt with having, knowing our grams, we've dealt with knowing moles, but here we have been given a pressure, temperature, and a volume. Well, we need to get to either grams or moles. We need to get to an amount. So how are we going to get to an amount? We are going to use our good friend, the ideal gas law. So we have a pressure, we have a temperature, we have a volume, we can calculate the number of moles. This would be great if it was at STP, but it's not at STP, so we're going to have to use ideal gas law. So let's plug in what we know. So we have been given the pressure, that is 815 torr. We have been given a volume of 75 milliliters. I'm going to convert this to liters, so I'm just dividing by 1,000. Now, be careful here that you don't lose any sig figs. So this 75 milliliters has 4 sig figs, so you want to make sure you keep those 4 sig figs when you convert to liters. Just as an FYI, we're going to calculate our number of moles. We need an R. So this is why I converted to liters, because I know I can get an R value that has torr and liters in it, along with mole K. So this is our R value. That is 62.36367, and that is liter torr per mole K. Now, you could also have taken this torr and like converted it to atmospheres. If you're used to using that R, that's totally fine. I like to change my R to fit what units I have. But you can always fit the units you have to the R that you prefer to use. It's totally fine. All right, our temperature now, again, we have to be careful with our temperature. Remember in R, our temperature is in Kelvin, but right now our temperature is in Celsius. I'm going to put this in a different color. Let's just convert that 25 degrees Celsius into Kelvin. So we just add 273.15, and that gives us 298.15 Kelvin. Okay, we did an addition subtraction, so we're going to have to make sure that we're going to use our addition subtraction rules when we go back and talk about sig figs. So I just want to give you a little heads up on that. We've got some mixed operations going on. Okay, so our temperature is 298.15 Kelvin. Let's make sure units are going to cancel. So our torr cancels, our liters cancel, our temperature cancels. We're left with moles, which is exactly what we want. So let's calculate that. So our number of moles, let me see what the calculator spits out. Again, lots and lots of decimals. Moles, and specifically this is moles of sulfur dioxide. So I do want to be careful that I'm not just throwing it out as moles, but I am specifying it is moles of which species. It is moles of sulfur dioxide, because especially in these longer calculations you get moles kind of all over the place and they're for different species and it's easy to get them mixed up. Now let's do sig figs. Okay, first I'm going to talk about our addition problem here. So remember, when you're doing addition subtraction, you're not looking at overall sig figs, you're looking at decimal places. So I have 2 decimal places in my 25, and I have 2 decimal places in my 273.15. So my answer also needs 2 decimal places, which means I am rounding at that 5. So I have rounded right there, which means this is 3, 4, 5 sig figs. My R has 1, 2, 3, 4, 5, 6, 7 sig figs. My volume here is 1, 2, 3, 4. Again, it's really important that you keep those zeros there. They were given right there. They are significant. And my pressure is 1, 2, 3, 4. So if you forgot to keep your zeros there, you would be rounding to the wrong number of sig figs. So again, just be careful with those zeros and know which ones are significant and which ones are not. So it looks like 4 sig figs is where we need to round. So 1, 2, 3, 4. So we're going to round at that 7 eventually, but not yet. Okay, so we now have an amount of sulfur dioxide. We are ready to use our percent yield. Now, if you like to always use grams in your percent yield, you can take this moles of sulfur dioxide and convert it to grams and calculate your theoretical yield in grams. It's absolutely, totally fine. However, percent yield can also be actual moles over theoretical moles. The important thing is you're not mixing up your units. So you can't take moles of sulfur dioxide for your actual and grams of sulfur dioxide for your theoretical. Your units have to match. That is the critical thing. So I am going to leave sulfur dioxide into moles, and I'm just going to calculate a theoretical yield that will come out in moles of sulfur dioxide. I will show you how this works. So you still have your percent yield. Same as always. It is actual over theoretical. Oops, AL times 100%. We know what our percent yield, where was it? Here it is. 72.35%. Okay, our actual yield is what we just calculated. Remember, this came from the problem. This told us how much sulfur dioxide was actually collected. So I'm going to put that in my numerator, 287. Again, I am not rounding yet because I don't want to introduce rounding error. That is moles of sulfur dioxide over my theoretical, which I will calculate. And let me squeeze in my times 100%. That is an SO2. Okay, so all I'm doing is just like before, I'm solving for my theoretical yield, except the difference here is it's going to give me a theoretical yield in moles of sulfur dioxide. So that is, where did I put that calculation? Here it is. Okay, so our theoretical is 4.53352 times 10 to the negative third, and again that is moles of sulfur dioxide. Let's talk sig figs before we move on to the next part of the calculation. So we rounded to this 7, that's our sig figs, which means our numerator has 4 sig figs. Our percent yield also has 4, and of course our 100 is exact. It has infinite, so we need 4 sig figs here. 1, 2, 3, 4. So I'm going to round to that 3. All right, now that I have moles of sulfur dioxide, I'm trying to figure out how much of each of my reactants I need. Let's do the easier one first. Let's do the bornite because that goes to grams, and that's going to be a lot easier. Okay, so starting with my moles of sulfur dioxide, let me switch colors here. 4.53352 times 10 to the negative third. This is moles of sulfur dioxide. So now I'm just doing straight up simple stoichiometry. I'm going all the way back to bornite. So the first thing I need to do is use my mole ratio. So I have 6 moles of sulfur dioxide to 2 moles of my bornite. Okay, that's Cu3FeS3. Okay, so that gets me to moles of bornite, but of course I need grams. Yes, here's where it asks for grams. So I need my molar mass. FeS3, and that is 215.586 grams of bornite. And now I'm ready to plug in. So put this in my calculator and I get 3.25788 grams. And then for my last step here, sorry, squeeze that 3 and I'm going to have to do sig figs. So I have rounded to this 3 here. That's 4 sig figs. My mole ratio has infinite and my molar mass here has 6. So I need 4 sig figs, which means I'm rounding at that 7 right there. So So let's get our final answer with the correct number of sig figs. 3,238 grams of bornite. Okay, great. Let's make sure there are no questions. No questions so far. Now we need to go back and we need to deal with our oxygen. All right, so our oxygen poses a little bit more of a problem because it's not asking us for grams of oxygen, it's asking us for the pressure of oxygen. So we need to know how much to put in, but we're not measuring an amount directly. We're measuring a pressure, which means we're going to get to use ideal gas law again. So just looking at ideal gas law, we're going to need pressure, volume, moles, and temperature. Okay, so we're looking for pressure. So we know that that is going to be our variable. So we shouldn't know that yet. We should be solving for that. Are we going to know our volume? Yes, because we're assuming the volume of the vessel is the same. That's at 75 milliliters. Do we know the number of moles? We do not know the number of moles of O2, but can we get to the moles of O2? Well, we can get to the moles of O2 doing our stoichiometry, except this time we went to bornite, so we're going to go to moles of O2 using our stoichiometry. Okay, so we can find N. We always have R. Do we have a temperature? And yes, because we're assuming the temperature is constant, so we're still going to use this 298.15. So we do have everything that we need to plug in to find pressure. What we have to do first, though, is we do need to calculate our number of moles of O2. Again, this is why it's important to label, because we do have a moles of sulfur dioxide here, but you want to be careful not to use it. That is a moles of a different species. We need moles of O2, not moles of SO2. So let me get one more page up, and let's do this calculation. So again, starting with my moles of sulfur dioxide, doesn't start with a 5, it's 4.5. 4.53352 times 10 to the negative third. This is our moles of sulfur dioxide. So let's do our stoichiometry and let's convert to moles of oxygen. Now the nice thing here is we're just doing one conversion. This is moles of O2. So let's double check and make sure I got that mole ratio right. So there were 6 here, and yes, there's 7 there. Because we're going into ideal gas law, we're just going to stay in moles. So there's no converting to grams, there's no converting to milliliters. We're just staying straight in moles. So doing this calculation, we get 5.289107 times 10 to the negative third. Again, this is moles of O2. So we've converted from moles of SO2 to moles of O2. See, these cancel out. Sig figs. All right, so our moles of SO2, we were rounding at that 3, so they're 4 sig figs. Of course, our mole ratio has, I can't write infinity anymore, as an infinite number, so we should have 4 sig figs here, so I'm going to round it at 9. Okay, sig figs are done for that step at least. Now I need to go back to ideal gas law. PV equals nRT. This time I'm solving for pressure because that's what the problem asked me for. So I know that pressure is going to stay a variable. My volume, again, remember it was 75 milliliters, but I'm going to convert that into liters, but I'm not going to drop those significant zeros. There we go, and that is liters. We just figured out our moles of O2, so I'm going to pop that in. 289,107 times 10 to the negative third. That is moles of O2. And let's see, I think, you know what, it doesn't specify what pressure, like what unit. But just to change things up, let's predict this pressure in atmosphere just so we practice using a different R value. So this is going to come out in atmospheres, which means I want this value of R. That is liters atmosphere over mole K. This is the value of R that you're probably most familiar with, that you see most often. And last but not least, I need my temperature. Again, my temperature stayed the same, so that is 298.15 9.15 Kelvin. Okay, yes, everything is in. We can plug and chug and solve for pressure. So let's solve for pressure. That is going to be 1.67331. It's going to come out in atmospheres of O2. Now, I should have maybe checked my units before I actually did the calculation, but we'll do both. We'll check units and we'll also check sig figs. So let's do units first. So liters have canceled. Moles have canceled. Kelvin has canceled. We're left with atmospheres. Bam, that's perfect. Now let's talk about sig figs. We have 4 sig figs in our 0.075 liters. Again, we rounded that to the 9, so we have 4 sig figs in our moles. Our R also has 4 sig figs, and our pressure. Our temperature has 5 sig figs. So we're definitely limited to 4 sig figs, which means we're rounding right there. So our final answer is 1.673 atmospheres of O2. And that is, let's just make sure, what pressure of oxygen. Yes, so we have calculated our grams of boronite, and we have calculated what pressure of O2 we need to add to the vessel. So this problem is now complete. Let's make sure there are no questions. So that was a lot of math and a lot of keeping things straight. Again, when you're doing stoichiometry like this, there are usually a couple ways to get to the final answer. I, tend to like to stay into moles, but again, you don't have to. You just need to make sure you get to the correct final answer. So if you're working with a friend, you guys might take slightly different paths. As long as you get to the same final result, either path is totally fine. That's the beauty of math. It can be done in multiple ways. So I hope you found this live stream helpful. Of course, as always, we want to know what is going to be most helpful to you. So you can request any topic for a live stream that you would like to see. Just contact me. You can leave a comment in the comment section. You can email me. You can contact me. You can leave a message on Facebook or YouTube, however you want. Just let us know what you'd like to see. Thanks so much for watching. I'll see you next week. Bye.